Testing, testing, 1, 2, 3. Hello, hello, hello. Good. Excellent, in fact. How's everybody doing today? Hopefully you're doing all right. On this fine May 18th, 2021. Yep. I don't think we have anything really in terms of announcements to talk about today. We covered pretty much everything yesterday, so might as well just get right into our topic for today, which is good because we didn't quite manage to finish off topic 5. But that's okay, because topic 5 is kind of extreme in its amount of bulk, shall we say. So, when we were leaving off yesterday, we were talking about the memoization of the Fibonacci sequence. Just to recap that very quickly, the Fibonacci sequence, if you try to calculate out the numbers in the Fibonacci sequence, the problem that you run into using a recursive algorithm to do this is that for every Fibonacci number that's not a 0 or a 1, you actually require 2 recursive calls to the same Fibonacci function in order to calculate any particular element in the sequence. This means that if you follow this down and try to calculate out, if we acknowledge the recursive nature of this recursive data structure, this means that every intermediate result that's required to calculate everything except for a 0 and 1 is going to produce a tree of calls, and the size of this tree blows up quite precipitously with increasing numbers of n, to the point where if you, on my personal computer, when I hit around the 35th Fibonacci number, it starts becoming noticeably slow to calculate because it's performing millions upon millions of calculations. So, our solution to this problem was to keep track of intermediate results using a procedure called memoization, which is a sort of subset of a more general procedure called dynamic programming. This hinges on the observation that when we have this tree of Fibonacci values that we're trying to calculate, a very large number of these will be repeats of things that had been previously calculated. And, because they are repeats of things previously calculated, we can, rather than calculate them many, many times, simply record whatever value we came up with and then substitute that for a recursive call, which is essentially what the memoization area of the algorithm does explicitly. If n-1 not in memo, then the memo, then we add it to the memo using assignment and make the recursive call. And then, rather than having recursive calls in the return statement explicitly, we simply make reference to the memo, which will now have all of the values we need if it didn't have them before. So, using this strategy, we can turn the runtime, the exponential runtime of the Fibonacci sequence, into a roughly linear runtime, which is a huge improvement. Generally speaking, in algorithms research, if you can take a exponential, if you can take any exponential algorithm and turn it into a linear algorithm, you're doing well. That is good feels territory. So, let me see. The weather is beautiful. It's absolutely beautiful. I agree. Let me see if I've got more people talking than I can see. Nope, everybody's just quiet today. Only got 22 people? Wow. Is there like a midterm or something? Or is it... Have people just kind of decided that, you know, there are things they'd rather do with their Tuesday morning, I suppose. That's fair enough. So, Lord knows I wouldn't be doing this if I wasn't getting paid for it, so... That's the kind of joke that you get with Mr. Moore's programming classes. So, so let's talk about something completely different now. And now for something completely different, we're going to talk about searching algorithms. So this relates back to, if you remember a few lectures ago, we were talking about linear search, right? Or, you know, the brute force approach to searching, the searching algorithm that is used, in fact, by the in operator that, you know, you may have used a few times in Python so far. So we're going to talk about a different type of search that makes use of some of the properties of the data. So you may have been noticing that as we talk about these more advanced algorithm type topics, increasingly we are relying on properties of the data, right? So this is actually a very key thing in programming in general, as well as algorithms specifically. It's always not like, it's not so much the stuff that is declared explicitly, like data types, right? Or, you know, whatever the variable's name is. Often, what is even more important than, you know, the explicitly declared stuff is the implicitly declared stuff. And I know I've been beating the drum for weeks now that you should try to make whatever's implicit as explicit as possible, because that's good design. You know, if you can't do that with code, you should do that with comments, for sure. And this still applies. But what is often most important about the data that you're working with is not what is explicitly stated about it, but what is implicit about it. Things that aren't necessarily, you know, properties of data that are not necessarily right there on the surface for you to observe. One such property that we're going to get into is the idea of sortedness. So, given a linear data structure, whether you can easily evaluate the elements of a linear data structure, like a list, for example, to see if they are quote-unquote in order. Normally, what is meant by order is in the numerical sense. Can I bring up Python? There we go. If we're in numerical order, that's reasonably intuitive to figure out. It just means, is every element of this list less than or equal to the element coming after it? So notice I said less than or equal to. So if I had like 3 3s in the middle here, this would still be a sorted list, right? Because every element is less than or equal to the next one. You know, you could say that something that is in reverse order is still sorted. So, you know, if you start high and go low, that is also, you could consider that to be sorted as well. It's sorted according to a different sorting scheme, right? In this case, each element is greater than or equal to the element that comes after it. However, this is still sorted after a manner of sorting. If you want to get right down technical with it, whenever somebody asserts something as being sorted, one should always ask the question, sorted according to what, right? Generally speaking, if no sorting is specified, right? If you just hear this is sorted data without hearing what it's sorted according to, you can assume this first one, that it's going from small things to large things, which I believe is ascending order. So this is fine. This is fine with respect to numbers. Numbers are reasonably intuitive to sort. If you're trying to sort strings, in general, the strings will be sorted according to one of two schemes inside of a computer, right? You will, in general, either have them sorted according to their ASCII values, or you will have them sorted according to lexicographic order. So ASCII values, of course, you'll remember that every character has a ordinal value. So the ordinal value of 5 is 53. The ordinal value of capital A is 65. The ordinal value of lowercase a is 97. To some degree, because capital letters come before lowercase letters, and because, the letters are ordered within ASCII notation, to some degree there is some overlap between lexicographic order and ASCII ordering, but, you should not assume. You should not assume that those are exactly the same thing, because they're not. So, lexicographic ordering, incidentally, is the same thing as dictionary ordering. So the same way that things are ordered in the dictionary. So anyway, so why am I talking about sortedness so much? Well, it turns out that if we're dealing with sorted data, we can make assumptions about the elements in that data set that allow us to write more efficient algorithms to do things like search that data structure. So we're going to go into a searching algorithm called binary search, which relies on the data structure it's searching being sorted, because it uses sortedness properties of the data structure in order to in order to make the thing more efficient, as we'll see. So let's get there. So search. Suppose we have a sequence of length n, and we want to know if a particular element is in the sequence. How many entries of the sequence do we have to check to find it, or to know that it is not in the list? That's the other thing about a search, of course, is in the worst when we're talking about the amount of time that an algorithm takes to execute, we often consider best case scenario, worst case scenario, average case scenario. So talking about linear search, the best case scenario for a regular brute force linear search, the way that we dealt with searching previously, is if the thing we're looking for is the first element we check, right? Then we only have to check one element. The number of elements that we need to check is in no way proportional to the size of the data structure that we're checking. It's because we happened to hit upon the one we were looking for on the first try. So that's the best case scenario. The worst case scenario is that we have to check every single one of the things in the data structure, and then we didn't find it, so we return like a false value or something. But we have to check every single thing that's in the data structure. So in that sense, the worst case scenario means that you have to perform n checks, where n is the size of the list that you're checking, right? In the average case, one might say something like, you have to start making some mathematical assumptions, like assuming an even probability that the thing you're looking for is any one of the things in the list. Then you might assume that on average, you would have to check half the size of the list before, finding the thing. But at that point you start getting into stochastic analysis, and it gets significantly more complicated from there. It's often much easier to pick out the best and the worst case scenarios. So, of course, linear search is also known as unstructured search. The idea with it is that we go through each element in turn and evaluate its equivalency to the thing we're looking for. If we find that it's there, then we can output a true or a false value. Unstructured search is, of course, relatively straightforward. The one thing I didn't open was get it. So, yeah, get it, topic 5.py. There we go. So, let's see. Let's no longer have an infinite recursion in this file, eh? Def, lin search. Takes some data structure L and some element E for X in L. I'm going to do it slightly differently than this guy. Since we're in the previous example, we wanted to know at what place in the data structure the looked for element is. In this case, since we're just returning a true and a false value, we don't actually have to know what the index is, so we don't need to keep track of it. We can just use a for loop over the elements in the manner that you might be disposed to intuitively. So if x is equal to e, return true. If you manage to get through that entire loop without ever returning true, then you want to return place, by which I mean false. I often misspell false as place. So, relatively simply, if we perform linear search over some data structure some list of randomly generated numbers between 1 and 10, or between 1 and 9, I suppose. Linear search of x for 2 or 3, let's say 3. Python 3 topic 5.py. True. 3 is in there. Ta-da! There you go. So that's linear search. Of course, we can, in the same way that we counted the number of recursive steps to, find if we had an efficient recursive algorithm, we can count how many loop iterations we have to see if we have an efficient loop algorithm. So global C plus equals 1, print C, loop iterations equals C. So, in this case, it took 6 loop iterations to find 3. 1, 2, 3, 4, 5, 6. Ta-da! There we go. So, this is fine. Unstructured search is sometimes called linear search because it goes through the sequence in a linear fashion. Also, its runtime is linear on the list size. So, when we describe algorithms, you'll often hear computer scientists speak about an algorithm being linear on the input or exponential on the input. What that means is that the runtime, or the memory, increases proportionally to whatever function that is applied to the input. So when we say that the output, or when we say that the runtime is exponential on the input, what we're saying is that the amount of time that the algorithm takes to execute is proportional to, for example, 2 to the power of the input size, right? And input size, sometimes that can vary. Sometimes we're talking about the value of the number, as in the case of the Fibonacci numbers. Sometimes we're talking about the number of elements in a data structure. That's actually a much more common use of that term is to mean the number of elements in a data structure, because very often, as you're going to see, these sort of trite numerical examples are not often the practical ones. The practical examples are often, can you process this over 1 million, tweets on the Twitter database or something like that, right? Like, large amounts of data exist in the world, and it's useful to be able to process them quickly. So, anyway, so let's move into how this changes if we can assume that the data is sorted. So, if the data is sorted, then we can make the assumption that every element in the list is less than or equal to the element that precedes it. Or, the element that follows it. So, if I were to pick the 4 here, I know that anything before the 4 has to be less than or equal to the 4. And everything that is above the 4 must be greater than or equal to the 4, right? Because, think about this 3, right? This 3 has a 3 before it and a 3 after it. So, just because this 3 here is less than or equal to everything above it does not mean that it's greater than everything behind it, right? Because you have to examine each one of these. The same property holds for the 3 that's immediately before it. So, so you've got possible equivalency across the entire list. Like, for example, a tuple containing only the number 1 is also technically sorted, right? But anyway, I digress. So, this algorithm is probably going to remind you somewhat of the Newton's method example that we covered right at the beginning of the course, and that we talked about a little bit subsequently. So we're looking for a particular value, right? We can easily pick out the middle of a list, right? The middle element of a list. If we compare the middle value of the list, there's a bumblebee trying to get into my house through the windows, and it's not working very well for him. No flowers in here. Go pollinate some of my go pollinate my crabapple tree, please. Anyway, the middle value can be compared to the value you're looking for, and we can make certain assumptions, or we can not make assumptions. We can draw inferences from the known properties of a sorted list, and, for example, the fact that this 4 is less than or greater than the number we're looking for. So, essentially, if we're looking for example, the number 6, and this 4, and we examine this 4, which is roughly speaking in the middle, if the number here is less than the number we're looking for, we know that the number we're looking for, if it exists at all, is going to be in the upper half of this data structure. Conversely, if this number is less than the number we're looking for, we know that the number we're looking for is going to be in the lower half of the data structure. And of course, if the number we're looking for is exactly equal to the number in the middle of the list, then we have happened to find it. This is what's known as the binary search algorithm. So def bin search. There we go. Takes the same inputs as linear search. We'll declare global C as well, just so we can take a look at how many times it takes this thing to execute. So, what was I saying? First, we need to find the middle entry. So midpoint is equal to L at the length of L integer divide by 2. Cool. If E is less than mid, we'll do something. L if E is greater than mid, we'll do something else. And else, the only else remaining is if they're equal to each other. Then we can return true because we know we've found the thing we're looking for. So, if we know that the element we're looking for is in the top half of the data structure, then we can recursively perform binary search on a subsection of this list. So we can perform binary search again, looking for the same value, on only this portion of the data structure. So, return bin search over some slice of this list and E. Similarly, we can return bin search over some different slice of the list, looking for E. So if the element we're looking for is less than the midpoint, right? So if the element we're looking for in this case is less than 4, we know that it has to be in the lower half. So we will start at the beginning of the list with this slice. So we'll leave that blank, and then we will go up until this guy. So we want to exclude this one. So we will just use the length of L integer divide by 2. We'll use the same address as the element that we're testing for. So there we go. And conversely, if the element we're looking for is greater than the midpoint, we know it's in the top half. So we will want to search over a subsection starting with the midpoint element plus 1, right? We know that it's not this one, so we'll want to start at the one that's one up from it and go until the end of the list. So there we go. Now, this is all well and good, but for this recursive algorithm, we need a base case, right? This all is the iterative case, although this branch of the iterative case doesn't actually have a recursive call in it. Both of these guys do, and so we've kind of missed the part where we return a negative result, right? Another way to say this is, what happens if binary search doesn't find the thing it's looking for, right? If you just leave it like this, it'll be an infinite recursion, which you don't want. So let's put a base case in there. So what is the simplest data structure? The simplest data, well, you can take two approaches to this. It's either a data structure that only contains one element or a data structure that contains no elements. Both of these would work. Let's use the one that contains no elements, just because that might be fun. So if L is equal to an empty list, then we know that there is no possibility that the element that we're looking for is inside of it, right? So we can return false. And we can make that check before we get to the recursive case. There we go. So let's actually do this. So x is equal to actually, you know what? It would be even better to do this in Python Tutor, because then we can see stuff in junk. So x.sort, let's just see if that works so far. Is x sorted? X is sorted. Okay, good. Now this is going to be, you know, relatively trivial, but that's okay. No, I think I'm gonna generate different data here. That'll demonstrate a little bit better. Not m, comma. Cool. So the data structure that we are looking for looks like this. 6, 7, 8, 8, 12, 14, etc., etc., etc. We got two 34s in there. So let us print the bin search result over x, looking for the element, shall we say, just for the sake of argument, 64. And now, then we'll do it again, but we'll look for something that isn't in the list, like 15. So we've got our bin search algorithm. We now open up a stack frame for the bin search function. The element we're looking for is 68. So the midpoint of this guy is 34. So if you take a look, we've got 15 elements. So the length would be 16. 16 integer divided by 2 is 8. So we'll be looking at the 8th element. So, or the element at index 8, so that's 34. 34. That's the midpoint. Ooh, you know what? I'm going to do something a little bit crazy. I'm just going to do this quickly so that it's a little more explicit in the visualization. I want it to show us the actual slices, because that would be useful. Oh. L2. There we go. So, we find our midpoint. So, is E less than the midpoint? No. Is E greater than the midpoint? Yes. So then L2 becomes the top half of the data structure. Right? Good. So now we have to open up a new binary search frame, because we're calling it recursively. This actually visualizes it beautifully. I'm very impressed with this. So the midpoint of this guy will be 73, because 6 integer divided by 2 will be 3, so element number 3 is 73. Is 68 less than 73? Why, yes, it happens to be. So our L2 becomes the front half of this. So these three elements. 36, 47, 68. Very good. we open up a new stack frame using this list as our as the list that we're searching over. The midpoint is set 74 or 47. So the midpoint being 47, we we take the top half of this very small list, and now we have a list containing only one thing. And of course, the midpoint of this list will be that self-same element. So we now have a situation where our return value is true because the element has been found. Now, so this is the binary search executing. Very good, very cool. So, the important thing to note about this, right? If you compare this to linear search, right? Linear search would have needed to check every element between 0 and the element we were looking for to find the element we were looking for, right? In this case, we would have had 11 entries to, 12 entries to check. However, in this case, we are performing no more than 1, 2, 3, 4 checks. I mean, if you count these guys, then, it's slightly more than that. But, neither here nor there. So, what's important to note about this is that the number of elements in the sublist that we're searching is reduced by a factor of 2 every time we recurse this algorithm, right? So in 4 steps, we've managed to go from 16 elements to 1 element, right? If we had 32 elements, we'd only need 1 more iteration, 64 elements plus 1 iteration, 128 elements plus 1 iteration, 256 plus 1 iteration. So in that, so our runtime, the number of times we have to run this algorithm to find the thing we're looking for, although it's a more complicated algorithm than linear search, the number of times it has to be run is proportional to the logarithm, the base 2 logarithm of the number of inputs. Now, if you consider how fast a linear function increases versus how fast a logarithmic function increases, the logarithm is going to beat the linear algorithm over time by an enormous factor. It's just, it's simply a matter of allowing it to run a sufficient number of times. So this is very, very cool. This is a very good optimization. And, we'll just display how this works if you can't find the thing that you're looking for. So if the thing that you're looking for is not, is not the last remaining element in the list, then you end up passing an empty list on to the next iteration. Now, because the empty list has been found, it should hypothetically be abutting, it should be executing that return statement. Does it, though? Oh. It might not be, actually. Might have a mistake there. But anyway, mistakes that I make aside, this is the essence of binary search. close that. Cool. Are there any questions about any of that? We'll go through the slides and demonstrate basically the same thing that I just showed you. So, if the list is sorted, then we can make use of this organization to make our jobs easier. The idea is we will assume the list is sorted in an increasing order. We look at the entry in the middle of the list. Again, if it's greater than the thing we're looking for, then we know that the thing we're looking for is in the top half. If it's less than, we know it's in the bottom half, and if it's exactly equal to, then we found it. So here's another example. This is an array of values, or a list of values, random but in sorted order. If we're looking for 33, 22 is less than, so we take the top half. 43 is greater than, so we take the bottom half. 29 is less than, so we take the top half. Precisely. So this is the version of this binary search algorithm that exists inside of the slides. They've got a special case for testing if the length is equal to 1. Yeah, actually, if I modify this guy, and rather than testing for the existence for equality with the empty list, if I just say length of L is equal to 0, that should, in theory, everything should be hunky-dory. Still no, huh? Index error. List out of index out of range. Oh, yeah, okay. I get it. This guy has to go down here. Because if... So L at 0 doesn't exist if the length of L is 0, right? So that's actually an error. So we get the false that we want. There we go. Ta-da! So. So a question from the audience is, what is the fastest searching algorithm? Well, I don't know. I don't know what the fastest searching algorithm would be. Algorithms research is like the kind of thing where there can be extremely efficient algorithms that are applicable only to very narrow use cases that you have no idea exist, right? I do not claim to be an expert in algorithms, so I would refer you to one of the professors in the department whose area of expertise is algorithms research. So, I don't know personally, but you can probably find it on Wikipedia if you look it up. Binary search is really, really good. Generally speaking, whenever you're dealing with, like, logarithmic runtimes, you're in the territory of, like, a good enough fast algorithm. The interesting one is sorting algorithms. I know a bit more about sorting algorithms than searching algorithms. But, yeah, it's interesting. By no means is algorithms research a settled science. The most efficient to date sorting algorithm, I believe was 2014 or 2012, maybe 2008. Sometime within about the last 10, 15 years, the most efficient sorting algorithm to date was developed. So, and sorting things has been a topic of algorithms research for since the 1950s. So, yeah, that's interesting, right? We don't really have time to get into sorting algorithms here, but if you take 1DM3, then you'll definitely get into it, I'm sure. So the binary search is a much, much faster algorithm than linear search because the number of things it has to check is proportional to the base 2 logarithm of the number of things in the list, as opposed to having to check every single one of them. So this is cool. The version that we're presenting here, though, in Python Tutor, this kind of this is still somewhat inefficient in terms of memory consumption, because you're producing a new list in memory each time when you slice the list, right? Like, that's one of the beautiful things about Python Tutor is when it shows you all of these lists actually exist as separate entities within the computer memory itself. Now, it turns out, just because of math and stuff, that the amount of extra memory that you'll need to designate to be able to produce all of these sublists will be no more than the size of the list itself. Ooh, you can move those around? Oops. Weird. Right? Like, it's kind of like a Taylor series, or one of those types of things, or Zeno's paradox. Yeah, so the amount of memory you'll need here will never be larger than this amount of memory, but you can still save all of that memory if, rather than reproducing copies of the list each time, you kept track of the beginning and end point of the bracket, and you moved the bracket in subsequently each time that you iterated the algorithm. That would be an approach that would be even more similar to the Newton's method analogy, the Newton's method one that we discussed previously. So if you were to do that, this is what it might look like. This does one interesting thing, which is it defines a function within a function. These are sometimes called helper functions. So in the same way that a variable that's declared within a function is scoped locally to that function, in the same way, if you declare a function within a function, that function is scoped to the function that it's declared in. So search3 helper will not be accessible outside of search3, right? But otherwise, you can see the only difference here between search3 and search2 is that search3 helper maintains a low and a high value, and these guys are updated in the recursive call rather than the list being modified. And they are also used to, of course, calculate the, what the midpoint is. Because the midpoint is, of course, midway between the high and the low point, the sort of bounds of the bounds of the brackets. Cool. So, let me see here if there are any more questions. Cool. All right. I think we will call a. Pardon me. We'll call a 10-minute break at this point in time. See you guys back here again at 10:29. Hello! Welcome back. I welcome myself back. How's everybody? Hope you had a good break. If you didn't, whatever. So, let's see. Chat rate. Playbacks. Okay. So, moving swiftly onwards. Just one little nubbin of topic 5 to finish off, and then we'll be on to topic 6. So, talking about functions as objects. So, we haven't talked about objects yet. Excuse me. But, essentially, in Python, everything is an object. So if I were to ask for the type of 6, it's class integer. If I were to ask for the type of a list, it's class list. If I were to ask for the type of, if I were to pardon me. Rip headphone users, right? Sorry about that. Actually, I want to hear how bad that was. It's terrible. I apologize profusely to any headphone users who might be in... Oh, thank you. Anybody who might be in the crowd. So, anyway. So in Python, because Python is object-oriented, everything is an object, right? So we haven't really got into objects yet, but here's like the Coles Notes version. Classes are to objects as function definitions are to function invocations, right? So a class defines what an object is, does, has. An object is an instantiation of that class. So 6 is an instantiation of the integer class. This list is an instantiation of the list class. That means it has all of the properties, attributes, and methods associated with lists, right, which are defined by the class. So if we define a function, do nothing, which literally does nothing, the type of do nothing is function, right? The difference between these two lines is if you call do nothing with brackets, that means you're actually invoking it. So it's actually running do nothing inside of this type evaluation. The return type of do nothing is none because it doesn't return anything. So that's why the class here is none type. However, if you just provide the function name without executing it, then you get class function. It is a function. So, what does this mean? This means that we can use functions like we use other objects of other types in Python. This means that functions can be passed around. So in the same way that you can provide a list as an argument to a function, you can provide a function as an argument to a function. Functionception, as it were. So this is an element of what is known as the functional programming paradigm, which is most exactly exemplified in the example of Haskell, the Haskell programming language, the great and holy mysteries of the Haskell programming language. Haskell is a purely functional language, and as such, any purely functional programmer will program purely in Haskell. Many other programming languages have seen the rise of Haskell, which has, Haskell has become prominent and popular in the last, 15 to 20 years. Other programming languages are like, hey, What's a Haskell language doing over there? That seems like that's really useful. Yoink! So Python has yoinked a couple of interesting features from the functional paradigm, and languages like Haskell, if not Haskell explicitly. However, that doesn't change the fact that Python is mostly still a procedural imperative language. It is an imperative language with a few functional decorations. So don't confuse it with a functional language which has no imperative decorations like Haskell. So, passing functions to functions. It can be extremely useful. If you ever end up programming with Haskell, taking something like 1JC3, one of the functions that you use most frequently in Haskell is called map. What map does is it applies a function to every element of a data structure. So, if we define map, which I believe I can just do here in this interpreter, L and some function f, for I in range, we're going to have the indexes here, range length L, I think you can omit the 0 actually, L at I is equal to f at L at I. This works, of course, because remember, this is passed by assignment, so L is an alias of whatever you put in there. So if we have x being something, and we define some function mult3, which takes some value q and returns q times 3, in a rather facile manner. If we map over x the function mult3 and then ask for what x is, every element of the list has had x. Every element of the list has been multiplied by 3. Bing, bang, boom. That's a mapping operation. And of course, the flexibility of this approach is that you can provide literally anything here. Any function here. So if we, for example, defined something kooky, return so times q plus kooky, and then we mapped this kookiness over x, you can see that you can see how kooky this is, right? It doesn't matter. It can be anything. Very cool. Yeah. I hope that your bleeding is sarcastic bleeding, not actual bleeding. If your bleeding there was actual bleeding and not sarcastic bleeding, then you had your headphones turned up too high. So that's not my fault. It's your fault. Please don't sue. I have my thing capped around here, so I tested it so that as I shouldn't be in the red for all everything except even the loudest sounds, which I won't test now, but responsible headphone use is also the responsibility of the person wearing the headphones. Incidentally, not that I'm trying to deflect too much blame, but so yeah. So that's what a map looks like. This is the type of thing we occasionally like to throw in as a test question, incidentally. It's a good test. The other thing that we should talk about a little bit is what's called an anonymous function. This is also a borrowing from functional paradigm. Anonymous functions, another way of thinking about it is as an inline function. So rather than going to all of the trouble of defining this, something like this is a perfect example, actually. Rather than going to the trouble of defining this function and, writing out the lines and, you might, like, if you're only going to use this once, this is an excessive amount of work to do, right? So, one thing that you can do, let me just restore X to its former glory. Cleanse it of kookiness. There we go. One thing that you can do is you can define a function all in one line. So the way that you do that is you say lambda, and then you write a colon, you write some expression. So, for example, q times 3, and then you... so the lambda operation, technically speaking, is a... it's like an argument extraction operation. So if you have an expression here, to perform lambda over this expression targeting q is to take q and turn it into an argument of this expression. Turn this into a function with q as an argument, which means that this thing is now a function that takes one argument, which means... there we go. It has this has the same effect as the mult3 function, named function that we defined above. Precisely the same. The interesting thing about lambdas is that they can use multiple, you can extract multiple arguments from them. So if I had some kind of expression, x to the power of y plus 3 or something like that, right? That's a function. If we apply arguments to it, we get an actual value, because this is a function. So you can use it like a function. Ta-da. There you go. So, that's about the long and the short of it for topic 5. Congratulations, we made it through. See me in court. Yeah? Oh yeah? Well, I don't have a good comeback to that, unfortunately. Something like something something. Well, obviously I would define myself because I'm a fool, and anyone who defends themselves has a fool for a client. Something something something. Anyway, so that's topic 5. So, is everything cool so far? Are you guys getting things? You know? Give me a thumbs up if everything's cool, if you guys don't have any questions. Yeah? Okay. Okie dokie. Well, I guess I'll assume everybody's fine then. You can put arguments. Yes. That's not really a question. Is there a emoji for hear no evil? Yeah, there is. There we go. Anyway. So, anyway. Moving right along. Oh, did I just, there we go. Can I put, arguments beside a lambda function? Yeah, actually, that's what I just demonstrated. These are the arguments, and this is the lambda function that they are beside. So, yes, that works. So, moving swiftly onward, let's talk about numerical computations. So this is a topic which is a little bit more numerical. It's a little bit more, shall we say, it's a little bit more esoteric conceptually, shall we say. But we're going to learn a little bit about how computers represent numbers and how we can use that to our advantage. So, we're going to talk about integers, real and fractional numbers, approximation algorithms, and floating point numbers. Real and fractional numbers are floating point numbers, incidentally. So, let's talk about integers. So, how do we represent numbers? How does the Arabic numeral system work, right? Well, it's all about place values, right? When we have a number, such as 2053, the way that that actually works is we've got 3 ones, 5 tens, 0 hundreds, and 2 thousands. So far, so grade 2. This works in, like, so this is the decimal system. This is how numbers work in decimal representation. It is a decimal system because the big conceptual leap on this slide is that rather than having 1, 10, 100, and 1,000 here, we have 10 to the 0, 10 to the 1, 10 to the 2, and 10 to the 3. This should indicate a pattern, right? The reason that this is called the decimal system is because the base here is 10. The base of this power is 10 each time. Decimal. Deci 10. Good. So, talking about the binary system now. So, you probably knew this beforehand, but all numbers in computers are represented by a series of ones and zeros. The reason that it's ones and zeros that represent things in a computer is because, fundamentally, at the level of the electronic circuits themselves, you have only a difference between high and low voltage, right? So inside of, like, a little transistor, transistors recognize either a high voltage or a low voltage. This is the difference between digital and analog electronics. In analog electronics, you have representations of, you basically have a continuous representation between 0 and however many volts of a number as, as a voltage specifically, right? And, this is how various transducers work. Like, for example, a temperature sensor or a pressure sensor will output voltage proportional to either the temperature or the pressure applied to the transducer. In the case of digital electronics, you have either a high or a low voltage with nothing substantial in between. digital electronics are designed to only handle high and low voltages. Because they only handle high and low voltages, we can use semiconductor transistors with them. Semiconductor transistors are able to be miniaturized to the point where they're just a few atoms thick, which is an incredible feat of engineering if you think about it. The fact that microprocessors exist is like, it's like that is the actual, like, far future technology that they were talking about in the 1950s that nobody actually appreciates. That nobody appreciates the fact that if you cracked open your computer and were able to crack open the CPU inside of your computer, there are pieces of machinery inside of your CPU that are so small that they are correctly measured by number of atoms across. That's absolutely bonkers. It's amazing anything works. But anyway, so you got high and low voltages, right? High voltages correspond to ones. Low voltages correspond to zeros. So in order to represent a number using only zeros and ones, we use the decimal system, or the binary system. Why does it say decimal here? That's wrong. The binary system. So binary, 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 binary. This is also known as the base 2 number system. The same way that in the decimal system, everything is based on a base of 10, in the decimal system, everything is based on a base of 2. So in the same way that you compose the number that you're trying to represent by multiplying out by the requisite place values, you do the same thing in the decimal system. However, you do the same thing in the binary system. However, because everything is base 2, rather than having this be by 1, by 10, by 100, by 1,000, you have it 1, 2, 4, 8, right? So in this particular number, 1101, is 8 plus 4 plus 1, which is, of course, 13 in base 10. Binary. There we go. Let me pop the chat out. I find that to be helpful. Actually, let me see. Can I do this? Yeah, there we go. So, I'm going to skip the question answer part as usual, but what is the decimal representation of the following base 2 number? You've got 011011. So let's do this out in my handy dandy thing that I use as a chalkboard. So 011011. So we've got the first one, that's 1. So 1 plus 2. The 4 place value is blank, so we skip it, or we provide a 0. The next one is 8, so 8, and then the next one is 16, and the next one would be 32, but it's missing, so it's a 0. So that's 16 plus 8 plus 1, plus 2 plus 1. So, of course, that's 3 plus 8 is 11, plus 16 is 27. Ta-da! So the answer is 27. You don't get it. What don't you get? Be more specific. I would love to answer your question, but I don't know, like, you have to be more specific than that, I'm afraid. So in general, pardon me, what you're trying to do is compute the sum of the relevant powers of 2, right? Multiplied by whether or not the digit is a 1 or a 0. So the way that Python in general represents binary numbers is using strings, which is kind of dumb, but that's how it does it. So let me just clear this guy out. There are a couple of ways of doing it, though. So, okay, cool. So binary numbers can be represented as integers by typing 0b and then a series of 1s and 0s, right? So if you take a look from our previous example, 011011 is 27. This is reasonably universal across programming languages, actually. So you don't have to worry too much about which programming language you're in. There'll be some equivalent of this type of representation. Sometimes it'll have like a quote here instead of a 0, but that's fine. Generally speaking, the way that Python likes to display binary numbers is as a string, however. So, for example, if we had the integer value 75, right, and we wanted to convert that to binary, you use bin 75. It gives you the binary representation of 75. However, notice that it is a string. It's a string. So there you go. So, but you know, if we took the string part away, then you know, there you go. And I believe if you take this binary representation, 75, assign it to some variable x, and if you were to perform integer conversion on it, it doesn't work. Okay. Base 2. Yeah, there we go. So, one little known fact about the integer conversion function, you can actually specify a different base system using the second argument. So if you're trying to convert from binary, you put a 2 here. If you're trying to convert from, for example, hexadecimal, which is totally a thing that you can do. Hexadecimal is a type of representation that we'll be talking about very shortly. If you want to convert that to an integer, then you use base 16, and octal is base 8. Again, we'll be getting into these different representations shortly. So, if you wanted to not use the handy built-in functions to be able to do all of this stuff, you would write a function that would look something like this. So, binary to decimal, we have b, which is a string containing 0s and 1s, not including, in this case, the 0b in front. D, which is our decimal number, is 0. For I in range from 0 to the length of b, if b is equal to 1, then d plus equals 2 to the power of the length of b minus 1 minus I. Because, remember, that when you're... so, in the same way that the numbers in the decimal system go from most significant to least significant digit, the same is true in binary. We go from most significant to least significant bit. Rather than call them digits, though, we generally refer to them as bits rather than, rather than digits. So, most significant bit to least significant bit. This is also sometimes called Big Endian, which is pardon me. That's kind of a funny, that's a funny little tangent about big versus little endian. So, I believe I've got this right, that big endian is most significant bit to least significant bit, because you start with the big end, right? That's actually a reference to Gulliver's Travels, the famous 18th century novel by Jonathan Swift, where the titular character Gulliver travels across the far reaches of the planet Earth in a time when very much the maps hadn't been finalized yet. And Gulliver, upon one of his travels, reaches a kingdom of the Lilliputians, who are very, very small people, no larger than the end of your no larger than your thumb. So he's a giant to these people. And it turns out that there are two sort of rival kingdoms of Lilliputians in this series of islands that he finds himself stranded on, and they have been locked in a religious war for a period of, some centuries. And the factions in this religious war arose because of a disagreement about which end of an egg it is proper to break to get at the egg inside of it. So you had the little Endians, who believed that it was correct to break the pointy end of the egg, and the big Endians, who believed it was correct to break the large end of the egg. Personally, I happen to be a side Endian, because I believe if you want to separate the egg, specifically, you need a reasonable cup to separate the egg with. So I'm a side Endian personally. But with respect to computing, that's where the terms big and little Endian arose, which is, just an interesting little parenthetical note. Anyway, so this is fine. This is a decent way of going about things. However, we can also make an observation that simplifies things somewhat. If you think about this in terms of an algebraic expression, we can collect like terms, right? So if you have, 2 to the power of 3, x times 2 to the power of 3 plus y times 2 to the power of 2 plus z times 2 to the power of 1 plus, w times 2 to the power of 0, right? 2 to the power of 0 is 1, so we can exclude that term entirely, but we can also begin collecting like terms, right? So that would become 2 times, and this is algebraic notation. This is, I guess I should be consistent in my terms, huh? So it's w plus 2 times all of this stuff, and you reduce the power by 1. This becomes 1 again, so you can delete that term. I should put a w there. You can perform this collection again. 2 times this stuff. That becomes a 0, that becomes a 1. We can exclude this term entirely because it's 1 multiplying by 1. And we can, even though it's a little bit ridiculous, we can collect the like terms once again, just to make things look a little bit more there we go. So this is a rearrangement of this guy, right? But it also implies a different sequence of operations from that covered in the previous, this guy. This is called Horner's rule. And essentially, what you can do is rather than rather than calculating each one of these terms separately, you can keep a sort of running total. In effect, what this does, if we have like a number 1101, for example, where x, this is x, y, z, and w, how that works is, you take this number, you multiply it by 2, you add this number, multiply all of it by 2, add this number, multiply all of that by 2, add that number, and you don't have to multiply it by 2 the last time. So yeah, that's another way of going about it, which is perfectly acceptable. Let's see if we have any questions. Cool. So, converting from the binary system into decimal is reasonably straightforward. Converting from the decimal system back into binary, that requires a little bit more thought. So, if you're paying attention here, you may notice that everything is revolving around these multiplications of powers of 2. So if we're multiplying by 2 a bunch of times to get stuff out of binary, then perhaps we divide by stuff a bunch of times by 2 to get back into binary, right? That's sort of symmetricality of mind. Of course, there's a particular manner in which we should do it. So it actually all revolves around the modulus operation. So if we have a number that we want to convert, like say this example is 13, but let me pick a different one just so that it's a better example, or possibly a different example. Let's do 19. Let's say we want to get 19 expressed in binary. Well, the first thing that we can do, whereas with converting the other way, we started with the big stuff and went down to the little stuff. In this case, it is easier to start at the little stuff and move your way up to the big stuff. So, in binary, the last binary digit, the least significant binary digit is always 1, right? Whether or not something has a 1 at the end is equivalent to determining whether or not it's even or odd, right? Because everything above the last element is multiplied by some power of 2, this last element is the only one that determines whether or not the number is even or odd. So if we can determine the evenness or oddness of the number, we can determine what the state of that last bit is. So in the case of 19, right, 19 mod 2, modulo is, remember, the remainder of integer division. That will yield us either a 1 or a 0, a 1 if the number is odd, and a 0 if the number is even. So, we know for a fact that the least significant bit here is 1. Cool. So we know, so we can, if we're keeping track of this on paper, we know the last digit is 1. So the question then becomes, how do we calculate the next one? Well, keep in mind this guy here, right? If we've dealt with w, right, how do we simplify things, right? Perhaps we divide by 2. Now, it's important to use integer division here and not floating point division. But, so this is division without remainder, right? So, and the equivalent way of saying this is, if I subtract 1 from here, and then move everything down by 1 bit, then what I'm effectively doing is dividing the whole thing by 2, right? So, it's also useful to think of this as a left shift or a right shift operation, which is bitwise. Like we're not going to cover bitwise operations explicitly, but you know, if you take all of the bits and shift them in one direction or in the other direction. You are effectively either multiplying by or dividing by 2, depending on which direction you're shifting in them. So if you divide by 2, then you are shifting them towards the least significant bit, which is, I believe, left shift. 19 left shift 1 is 9. Yeah, so there you go. This is left shift. This is right shift, I think. Anyway, 19 divided by 2, integer divided by 2, is 9. So now we have 9, right? We're calculating everything based on the number 9. These 4 bits in isolation must comprise 9. So 9 mod 2 is, of course, 1. So we know that bit must be 1. And we can further divide 9 by integer divided by 2 to get the next one. So that ends up being 4. 4 mod 2 is 0. So we know the next bit has to be 0. 4 integer divided by 2, I don't even need a calculator for this, is 2. 2 mod 2 is, of course, 0. 2 divided by 2 is 1. 1 mod 2 is 1. So the binary representation of 19 is 1001, which we can check by just entering it in, and you can see that we have it correct. So there you go. That's how you perform binary conversion manually. Generally speaking, this is... This is... You might be saying, okay, so why is he going through this? What's the point? What's the deal here? You know, since he's already shown us how we can use functions to do this, what's the point of going through this? And the point is there are 2 points to this. Number 1, it's important to understand how these things work conceptually, as well as to be able to do them practically. And number 2, the procedure is the same regardless of what base system you're working in. So, converting to hexadecimal follows the exact same procedure, except rather than using 2, you use base 16. Converting to octal works exactly the same way, except you're using base 8 instead of base 2. And one thing that I greatly enjoy doing to students on tests, and you'll see a little bit of this on the one assignment as well, is I like to give people exotic base systems. So, you know, can you convert a decimal number to something that's base 24 or base, 63 or something? Some base system that's very large, and that there's no algorithm for. Can you still perform this procedure on it? And that's a good test question that I like to ask sometimes. Yeah. So, good. Yeah, no, the number of, yeah. So as your colleague is asking, why did, 5 digits here, is it always 5? No, it's not always 5. The, if you continue dividing by 2 here, you just get a bunch of zeros, and, you would get a bunch of zeros here, and I just decided not to include them because they're not interesting. But they do exist. It's kind of like, in theory, every decimal number has a infinite series of zeros in front of it, right? Like the number 337 has an infinite number of zeros in front of it. The same is true in the binary system. However, in the binary system, we have, the binary system is implemented on computer systems. And computer systems have limited memory and do not deal well with the concepts of infinity unless they're explicitly told how to do so in terms of non-infinite things. So, the way that an integer is stored in your computer, depending on what type of integer it is and what programming language you're using, there will be a set number of bits that are given over to the storage of that number. So, in the case of most integers on modern computer systems, you will be using 32 bits to represent an integer. Even though we are dealing with 64-bit operating systems, for most purposes, integers are 32 bits, and long integers are 64 bits. Short integers are 16 bits. And that's not really a useful distinction in Python, but it's a very, very important distinction if you're programming in any other language, including C and C-based languages other than Python. But, so you may consider this to have 32 minus 5 bits, 32 minus 5 zeros in front of it, right? And that's like the actual, how it's actually represented in memory, right? And that's useful to know. So, gonna skip that. Or, you know, kind of, I've already done this procedure, but the point that this slide is making is that 0101001 is precisely and exactly equivalent to 101001, right? It's the leading zeros problem. Actually, when you're dealing with binary numbers in computing, it's actually reasonably common to include a number of zeros in front of it that sort of rounds it up to the nearest power of 2. So it wouldn't be uncommon for you to see a binary number expressed 000100011, because that comprises 8 digits. And because that comprises 8 digits, that's a comfortable computer number. I don't know how to say it other than that. In general, there's a strong preference among computers and computer professionals towards things that are things that have a base 2 number. And this is, you know, one of those. So, anyway, if you want to convert from decimal to binary, in terms of, like, putting the procedure that we just described into an algorithm, this might be one way of going about it. So we have a decimal number d. We start off a string as an empty string b. While d is greater than 0, if d mod 2 is equal to 0, then we append a 0 to b. Otherwise, we append a 1 to b. And on each execution of this loop, d becomes integer divided by 2. As soon as d is through, as soon as d is now 0, we quit this procedure and return b, the string. Very, very cool. You can also do this with a while loop, rather than not with a while loop. You can do this without the if statement, pardon me. So you can just perform string conversion on d mod 2 rather than using if statements to decide between different literals. You can have that calculated automatically, which saves you some lines of code. So that's all well and good. Let me see if we have any comments. Cool. So in general, in computer systems, there are a couple of other representations that you may occasionally have to deal with. Hexadecimal much more so than octal, but octal does show up every once in a while. So the observation was made by early computing professionals that while binary is accurate to the manner in which computers actually store information, it's kind of a pain in the ass to work with, because it's long and tedious, and there's a reason the decimal system exists, right? So you can imagine how if you had to work exclusively in binary, that would just become terrible after, like, you would get tired of that in about 5 minutes. In fact, it probably wouldn't even take 5 minutes. So, But, of course, we're also faced with the problem that decimal digits do not line up with binary digits, right? So, the binary equivalent of 9 is, these 4 decimal digits. The binary equivalent of 10 is these 4 decimal digits. You don't actually end up having to need another binary digit to add to these guys until you hit 16, right? Now you have 5 binary digits that you're dealing with. So these, the number of decimal digits does not have a straightforward relationship to the number of binary digits. And that's unfortunate because, it would be really nice if that were the case. It would make a whole lot of sort of low-level computing things more easy. So, we invented octal and hexadecimal. Octal is base 8. It can only represent digits from 0 to 7. And the purpose of octal is to represent numbers with 3 bits in them. So, you use lowercase o to designate an octal number. And so, octal 7 is 7, octal 1, 0 is 8, right? So the trick with this is that in binary, octal 7 is 111, right? And when we get to octal 8, octal 8 doesn't exist. Octal 01, that adds one more, where one place value has been added to the octal number, 3 more place values are added to the binary number. So each place value in octal corresponds to precisely 3 binary digits. That's a useful thing, right? And in the same way, hexadecimal uses 4. So hexadecimal, 7 is, let's do 8, is, this number. But once we add hexadecimal 1 to that, we're starting to dip into the next sequence of 4 bits. This is much more explicit. I can only do the same thing that I did with octal once I explain how hexadecimal digits above 10 work. So in binary, actually, let me just generate the range. So if we have the numbers between 0 and 16, right? Or, these are all of the hexadecimal digits. Right? If I perform, do I still have map in here? Yeah. So x is list range. I know it's break time. Just give me a second to round this off, please. There. So x is this guy, map over x, the hexadecimal conversion function. You'll see that the hexadecimal numbers, 0 through 15, go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then when we hit the equivalent of 10, we start with letters, A, B, C, D, E, F. So, the binary equivalent of hexadecimal F, I usually like capitals, is 1111. If we add 1 to that, we get one additional digit. So hexadecimal 88 is basically 2 of the it's 2 of these guys in sequence. So this is hexadecimal is generally speaking the much more preferred representation to octal, because hexadecimal digits, if you chain them together, you'll hit all of the sort of standard sizes for things, right? A normally sized integer, which is 32 bits in size, is 4 hexadecimal digits, I believe. Wait. Yes. Because it's 32 divided by 4 is 8. A short integer is 2 hexadecimal digits, because it's 16 bits. A long integer is 8 hexadecimal digits. So you can see everything lines up very nicely. Whereas, the number of binary digits that there are in a 64-bit integer is like, it's 2 to the power of 64 minus 1. That's the largest 64-bit integer that can be represented in unsigned arithmetic. So, anyway. Yeah, so one more caveat for all of this. Basically, everything that I've been talking about with respect to, mapping to underlying representations applies to positive integers only. There's a whole different system for doing negative integers, which we're not going to talk about in this course. Just keep in mind that it's different. So, anyway, we're going to have our break. We will have our second break. We will resume class at 11:36. See you then. Greetings! We return to this once more epic, wonderful, lovely stream full of epic, lovely, wonderful people. Present company excluded, of course. That's a joke! Ha! Burn on me. How's everybody? Hopefully doing well. I never know what to say. So I just kind of waffle. So, we have talked about integers. We are now going to talk about floating point numbers. Floating point numbers are more difficult to understand than the integers. So if you had problems with the integers, you're probably going to have more problems with the floats. So, so our conception of place value and how it applies to numbers extends on both sides of the decimal point. So this is a mistake. This should read 10, by the way. So if we had, rather than 2053, if we had 20.53, the imposition of the decimal point indicates the point at which we begin with negative powers of the base of the number system. So this number here is 2 times 10 plus 0 times 1 plus 5 times 1/10 plus 3 times 1/100th to yield 20.53. That's how things work in base 10. In base 2, things work the same way. So rather than, so when we go to, and I'm going to start calling these fractional numbers, not decimal numbers, because they are not in decimal. I'm probably not going to call this the fractional point. I will still call this the decimal point. Hopefully, I realize the terminology is somewhat ambiguous and confusing. Hopefully, we can all muscle through with our gigantic brains. So, if we have the binary number 11.01, that's 1 times 2 to the power of 1 plus 1 times 2 to the power of 0 plus 0 times 2 to the power of -1, which is 1/2, and plus 1 times 2 to the power of -2, which is 1/4. So rather than doing 1/10 and 1/100th, we're doing 1/2 and 1/4 and 1/8 and 1/16 and 1/32, etc., 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 all the way on down the line. So this has some interesting consequences, some very interesting consequences. So here's a question, and this sort of relates to things that we talked about earlier in the course. You remember I did that demonstration of how if you add 0.1 together 10 times, you don't actually arrive at 1, which is what you would expect in the decimal system, using things, if you were to do the calculation by hand, that's not what you would expect, right? And wherever there is a discrepancy between how you would do things intuitively or by hand and how the computer does things, that's worthy of exploration. So, how would you represent 0.1 in the rational decimal numbers, or the rational binary numbers, the fractional binary numbers? Well, it kind of depends on how many bits you give it. Assuming we had 3 bits to throw at it, we could get, we would have 0, 0, 1. That's as close as we could come to 0.1. It would be 0.125. That would be 1/8, right? Anything else would be further away. If we add 2 additional bits of representation, we get 0.00011. So that's 1/16 plus 1/32. 1/16 plus 1/32, that's 3/30 seconds, which is 0.09375. So you'll notice that this is closer to, but still not exactly, 0.1. So let's add 4 additional digits to this number. We end up with 0.000110011. That ends up being 51 out of 512, which ends up being 0.099609375, which, again, is much closer to 0.1 than either of the previous ones. But this is still not. We're still a ways off, right? This is still not 0.1. So it turns out that you can actually do this forever. You can continue to add bits to this binary representation, and you will never exactly hit 0.1. This is because numbers can have finite representations in one base system and infinite representations in other base systems. This is something you already know. You already know from, your career in mathematics so far that the number 1/3 cannot be represented as a decimal number with exact precision. It's 0.333333333333 all the way on down. It turtles all the way down. So, in the same way that 1/3 cannot be represented with with a finite number or inexact precision in a decimal number, 1/10 cannot be represented that way in the binary system. It turns out that in order for a number to have finite binary representation, it must be a multiple of some one of these binary fractions, right? And that makes sense, It has to be, if you take the numbers, half, quarter, 1/8, 16th, 32nd, and you iterate that out for as many bits as you have to represent these things with, your number must be a multiple of one of those in order to have finite binary representation. In the same way that in order for it to have finite decimal representation, it has to be a multiple. It has to be a multiple of either 1/10 or 100th or 1,000th or 1/10 gajillionth. You have to have representation there. So the interesting thing about that is that the binary system doesn't exactly represent everything that can be expressed in decimal. But anyway, so that's the reason That's the reason that 0.1 added 10 times together does not equal 1, right? Because when you write a floating point number in any computer system, including Python, you're not actually writing 0.1. You are writing 0.1, the approximation of 0.1 in floating point arithmetic that most closely approximates it. And we can actually see, I think we've got this, let me just skip ahead, there we go. So if we use the format command, 0.1 with 0.60f, that means 60 decimal digits, you can see that the way that 0.1 is represented is it's only accurate to, say, 16 decimal places? 15, 16? 17, 16, yes. So 0.1 is represented accurately to 16 decimal places. Past that point, basically we get random numbers until we hit the limits of finite. We hit the limits of the numerical representation system itself. Cool. So, yeah. Let me just run this back then. So, another question, which we're not going to do as a question because we're not in person. Which of 3/4 and 1/3 have finite binary representation? Obviously, it would be only 3/4 because 3/4 is some multiple of a base 2 fraction. 1/3 is not, and therefore does not have finite representation. In fact, 1/3 would be 0.01010101 all the way on down. So the question. This then begs the question: how many decimal places of precision do we keep then? Given that we are constrained to always using an approximation of the number rather than the number itself, how close of an approximation do we use? And it turns out this has been decided for us a long time ago. Way back in the 1970s, I believe, possibly the late 60s, we had the International Electrical and Electronics Engineers Association, the IEEE. I'm probably messing up the acronym, which is terrible, but that's okay, because the IEEE is like the the IEEE is a very, 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 very important organization within the realm of computing. The IEEE has several functions. Most academic conferences, or at least most big academic conferences in the area of electronics engineering, software engineering, even electrical engineering, they're going to be they're sort of funded and put on by, at least in part, the IEEE. The IEEE also publishes standards documents, which, to people outside of engineering disciplines, standard documents are kind of like these sort of arcane tomes of, miscellaneous stuff that's practically unreadable. If engineering was wizardry, then engineering standards books would be the spell books. That's sort of where the magic comes from. The IEEE publishes all kinds of standards, and it's because the IEEE publishes all kinds of standards that, things like the internet work. And I'll explain to you why the internet wouldn't work if it weren't for this particular standard that we're talking about right now. So the IEEE has a standard on floating point numbers. All computer systems that are compliant with the IEEE, are compliant with IEEE standards must be compliant with the IEEE standard on floating point numbers. This standard specifies how many digits have to be used to represent these fractional numbers. And, the interpretations of these bits within the sort of space in memory is also set forward in this standard. If this were not the case, then all kinds of different organizations all over the world would have different ways of going about it. And this was the case in the 1950s and 60s, right? Where they even had, representations of real numbers at all. The representations were not standardized. One of the only reasons that different computers by different manufacturers can communicate data, binary data, between themselves is because that binary data, the form of it, has been standardized by the IEEE. If ASUS had a different way of doing floating point numbers to Toshiba, then any number, any floating point information that was transferred from any ASUS laptop to a Toshiba laptop would be scrambled, right? That number would be garbled by the transfer process because Toshiba has a different interpretation of the underlying bits than ASUS has, right? That's what the situation would be. So the only reason the internet works is because all of these standard communication protocols, or all of these standard representations and standard communication protocols, have been set out by people who knew what they were doing. And one of these is the floating point number. So, following the IEEE standard, Python uses 52 binary digits to represent these numbers, which is approximately 16 decimal digits. So if we take the binary interpretation of 0.1, cannot be interpreted. Okay. All right, so it's not going to show us. But you could, there are online converters that you can use to look at the underlying binary representation of floating point numbers. Although that's not really very useful, but anyway. It's not as useful as it is with integers, because there's not as direct a comparison. But anyway, so these 52 binary digits come up to approximately 16 decimal digits. And, generally speaking, if you're in a science class and you're holding, 4 or 5 digits of precision, that's normally considered to be good enough for most purposes, right? So, it's not like the computer isn't holding a heck of a lot of precision in comparison to the amount of precision that most people are holding. The only thing is, because it's a computer and it must do things exactly, that once you get past that precision, you get into sort of this no man's land, where things are not exactly what they say they are. So yeah, and the standard within computers is to not display the entirety of the floating point number for obvious reasons. It's to display the sort of rounded off value to, X number of decimal places. So don't be fooled. So this sort of introduces an interesting characteristic of floating point numbers, which is that sometimes these... So because we're always dealing with imprecise numbers, depending on the numerical numerical operations you're performing on these numbers, sometimes these errors accumulate and sometimes they don't, right? And it's actually very difficult to tell which, like, in what circumstances you'll end up with errors and in which circumstances you won't. So, for example, if we have 1/3 plus 1/3 plus 1/3, we get 0.1. If we try 1/6 plus 1/6 plus 1/6 plus that a few more times, there we go. That is not printed as exactly 1. All right. So if we format this to display the remaining decimal places, you'll see that we get, like, this is what we get, right? Whereas if we format this guy, sorry, just bear with me for a moment. You'll see that in this case, the errors actually cancel out pretty well, right? This is actually a more precise representation. Well, okay. Sorry. I was going to say this was a more precise representation than this one is, which is true, but this is also 1.0 and not 0.1, so got to keep things in my brain. But anyway, so you can see in the case of 1/6, the error accumulates, but in the case of 1/3, the error cancels itself out. So the take-home message here is that it's actually impossible to predict with floating point numbers whether you will be in a situation where those errors are canceling out or not. Especially if you're dealing with variables, right? A variable might be any number of values. It's relative, like, you could, in theory, work the theory out to determine whether, these literal values will end up canceling their errors or not. But the number of times that you're going to be working with straight literal values is vanishingly small. Normally, you'll be working with inputs and outputs to functions and variables and, all kinds of neat jazz like that. So, the predictability is very low. The predictability of whether these errors are going to cancel. So, the net consequence of this is that equality comparison itself becomes a sort of a difficult thing to do if you're working with fractional or floating point numbers. So 1/3 plus 1/3 plus 1/3 is equal to, tests true if you compare it to 0.1. However, if you took 1/6 added to itself 6 times and tried an exact equality comparison with 1, you get false, even though it's, one might reasonably expect that to be true, right? So the whole issue then with this guy, the whole issue with this equality comparison is this is exact by the bit equality, right? Equality means exact equality. Exact equality is all well and good when what you're dealing with are whole integers, but when you're dealing with these types of approximations of values, exact equality is not going to be the thing you want to use. So there are various strategies for trying to get around this problem, but the most effective one is, rather than using precise equality, subtract one value from the other, take the absolute value of it, that's abs, use the abs function, it will get you abs instantly, and then you test to see if it's inside some epsilon. Epsilon being an error. So if the difference between these things is less than, shall we say, 0.00000001, you can be pretty sure that they are this is a reasonably precise, these things are reasonably equal, right? And, you know, you can add quite a few zeros to this before it becomes false. 15, in fact, because, you know, that's the representation. So you don't actually normally have to test to that level of precision. You can probably get away with, you know, 4 or 5 zeros. But, like, this will yield a result from the comparison operation that you want, where exact equality comparison will not. And this will work for all floating points at all times, right? So that's the take-home message here. If you're performing exact equality over floating point numbers, you're doing it wrong. Universally. So this is kind of a long way of going about it, but don't ever use exact equality comparisons with floating point numbers. Okay? Okay. Cool. So let's talk about floating point numbers more specifically then. Like, what is I've said floating point like 100 gazillion times during the course of this course, but we haven't actually yet described what a floating point number is, right? So a floating point number is, in essence, a binary representation of a scientific notation, right? So for those of you who may not be familiar, scientific notation is something like 4.576 times 10 to the power of some power of 10, like 5, right? This is scientific notation. You have a fractional component and an exponential component, and, you know, this is very common when you're dealing with, you know, chemistry or physics or something, you know. If you're dealing with the amount of charge on an electron, like, it's given in scientific notation, right? So scientific notation, the whole purpose of scientific notation is to not have to include large numbers of zeros, right? You can get a good idea of the magnitude of the number by the exponent of 10, or the power of 10. So you don't necessarily need to explicitly write out all of those zeros. It gets tedious, right? So in the same way, with floating point numbers, we have a fractional component and an exponential component. The fractional component has a specific name. It's called the mantissa. And you have, you know, the exponential component is just called the exponent. So it turns out if you had to decide how many bits you would put into the fraction versus the mantissa, there's a trade-off there, right? That trade-off has been decided for you by the IEEE, but it's still important to sort of understand it conceptually. The more bits that you put into the fractional component, the more bits you're taking out of the exponent, right? You have a fixed number of bits going on here. There are 64 bits. One of those bits represents whether it's positive or negative, so we actually have 63 bits that we are trying to allocate between the fraction and the exponent, right? So if you give more to the fraction and less to the exponent, you can represent numbers with greater precision, but you would decrease the range with which you can represent them. If you increase the exponent component, you decrease the precision of the fraction, but you increase the range of numbers that can be represented. So it turns out that the numbers that were decided on is 52 bits get thrown into the fractional component, and 11 bits get thrown into the exponential component. This means that we can represent numbers from 1.1111111 base 2 times 2 to the power of 1023. That's the biggest number it's possible to represent in floating point arithmetic, all the way down to 1.0 times 2 to the power of negative 1022. So in terms of like absolute magnitude of the representation of floating point numbers, you can represent numbers from 1.79769, etc., etc., times 10 to the power of 308, all the way down to 2.225 times 10 to the power of negative 308. And if you know anything about numbers and how big they get and how small they get, 10 to the power of 308 is, a very, 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 very large number. One might even say probably larger than anybody would ever need. So, so that's basically what the decision was. Going any further than this was decided to be unnecessary, so they threw everything else at the precision in the fractional component. So yeah, so that's what floating point numbers are and do. Are there any questions right now? I'd like to take a moment to ask if there are any questions in the audience. If you wouldn't mind giving me a thumbs up or whatever, that would be, if you don't have any questions, that indicates to me that you guys are still alive, which would be good. It seems like our viewership has been remaining relatively steady today, but, maybe a slight decline over time. We had 50 viewers 2 weeks ago. We had 80 viewers 3 weeks ago. What's the trade-off again? Good question. So think back to this bit here, right? The more bits that we threw at the fractional representation of the number, the more precision that we were able to achieve, right? So if you increase the number of bits in the fraction, that means that you increase the precision of the number that you can represent, right? Whereas if you add bits to the exponent, that increases the power here that you can get to, right? So that increases the range of numbers that you can express, right? So that's the trade-off here. If you were to move this line a little bit more into the fraction, like if you were to take some bits from the fraction and add it to the exponent, you would lose precision, but you would gain range. And if you took some bits from the exponent and added it to the fraction, you would lose range, but you would gain precision. So, yeah, there you go. Which is actually what this says. The number of bits of the fraction limits the precision. The number of bits in the exponent limit the range. So there you go. Cool. So, so here's another interesting little tidbit for you. Because the precision of these floating point numbers is limited, it's actually it's possible for them to goof up in more ways than just this bit where if we add 1/6 together a bunch of times, it doesn't actually add up to 1. It's actually possible to lose numbers entirely because you've lost the precision. So if we have a whole bunch of 1s, and this is a floating point number, it's like 1 times 10 to the power of 60, right? If we were to represent that as a floating point number, you know, represented with reasonably exact precision. So the problem that we run into is, what happens if we add 1 to it? Huh? It's still the same. Right? The 1 is lost because it falls outside of the precision of the number. It's too small to be added to the number. That's another way of thinking about it. And that actually happens for a while with this one. So, there you go. If we add 100 to this number, we get, what is this, 1,128,000,000. We didn't even add 28 here. We added 100. So, that's another issue that we can run into with floating point numbers. If floating point numbers become very large and we add very small things to them, those small things get gobbled up. They get eaten up by the representation, and they end up either not even being represented at all, or if they're kind of a marginal case, they can be misrepresented in the floating point number. Now, again, you know, if you're looking at things in terms of absolute magnitude, this is not much in comparison to the, 128 is vanishingly small in comparison to, 1 quadrillion. But, if you actually want to know the exact number, then that's a problem, right? And it's interesting to note that this does not happen if you're using integer representations. With integers, you don't lose this precision, and that's because there's, with integers, you don't have to worry about precision, because it just, every single number has an integer representation. But with floats, it's a different story. So, floating point numbers are risky. Beware of them. A lot of really old computer games don't even use floating point numbers. Like, if you take a look at stuff that was done on the Nintendo Entertainment System, for instance, that's primarily done. Like, I don't recall many instances of decimals being used. Even games that would show you, like, fractions of a second were representing those as integers and then just, like, printing the decimal point on screen. So, yeah. So that's a problem. How do we get around this problem? Well, in Python, we've got two approaches, two ways that we can get around this problem. Number one is the decimal library. So arithmetic with the Python decimal library will produce the same errors as calculations by hand. That by default, 28 fractional digits are kept. The precision can be changed. So, rather than representing, so rather than using the floating point representation, we can use the decimal library to basically do the same thing. So, decimal, from decimal, import port, decimal 0.1 is actually 0.1. Now, decimal of 0.1 without the quotes is the decimal number as represented by floating point. So there's a difference. If you're going to use the decimal library, you must put this in quotes. Make it a string. Because if you throw a floating point number in here, it's just going to interpret it as a floating point number. This is already a float, so this is the float representation, right? However, if you want to represent 0.1 with exact precision, make it a string. If you make it a string, then everything works out. And you can actually perform arithmetic with the decimal library that it's impossible to perform with exact precision using floating point. Right? 0.3 versus 0.3 plus garbage. So the question is, all right, so why would anybody ever use floating point then, if this clearly superior alternative exists? First of all, it's kind of clunky to continue using the name like this, right? So it takes more to type, and that is a factor. Number two, the thing about floating point operations is that floating point as a representation has been around for a long time. Hardware manufacturers over the years have developed a number of sort of add-on modules that are inserted into your CPU that accelerate specifically floating point operations. So floating point operations used to be very expensive operations until specific circuits were developed and included in CPUs, which accelerate those operations. So floating point operations, although they're imprecise, occur very quickly in comparison to all other methods of representing decimals. Representing decimals is something that's extremely time-consuming to process. So, using the decimal library, I think, takes something like 3 times the time that using a floating point number does. So, you know, if it's an assignment that you're doing for this class, it's unlikely that that amount of time is going to be, you know, material to the execution of your program. However, as we saw with the Fibonacci numbers, sometimes runtime is actually an issue, right? So if runtime is an issue, then you probably can't use the decimal library, but if it's not, then you probably can. It depends on how patient you are. So there you go. You know, they used to measure the speed of processors in flops or megaflops. Flop stands for floating point operation. So megaflop would be how many million floating point operations per second can you process? You don't really hear people talk about megaflops anymore, but, you know. Anyway. Anywho, I think rather than get into the fractional library, we'll call it here today. If you have any questions, please put those into the chat now. Otherwise, we'll get going. Yep. I will take questions. What's the estimate for next week's viewer count? 25. Yeah. 25. It's an exponential decay, right? Yeah. It's kind of almost like we lose 1/3 each week. Can I go over why adding one number to the huge number didn't register? Yes, I can. So the issue here is that the number that we're adding falls outside of the precision of the floating point number, right? So essentially, this number would be lost in this junk, right? So, what's another way to say it? So let's imagine that you had a number that had to be represented with 8 bits, and in order to add to that, and you wanted to add to that a number that had to be represented with 9 bits, right? It turns out that what the computer does is it doesn't assume anything about the number that falls outside of the range, it just drops it, right? This is the same thing where if you convert a floating point to an integer, it just drops the fractional component. It doesn't round it, it just it drops it. So this is the same sort of thing. So if you add 1 to, a very large number that's a floating point number, that 1, well, I need it to be slightly larger then. There we go. This 1 falls outside of the range that can be represented inside of this number. It's outside the range of... It's smaller than the precision of this number. That's another way of thinking about it. In terms of analogies, if... let's say you had a charge. This is a good analogy. Let's say you were talking about charges. Like, if you know physics, each charge, the charge of an object, like static electricity, that type of charge, must be a multiple of the charge of an electron, because electrons carry the charge, right? So you can't have charges that fall outside of the precision represented by the charge of an electron. So if you tried to add charge to an existing amount of charge that was smaller than the charge of an electron, it doesn't make sense. It just wouldn't work. You couldn't do it. It's the same kind of idea. So yeah. Anyway, I've got an appointment to get to, so I'm going to call it here. Thank you very much for your time and attention, folks. We will resume next week. So take her easy, folks. On Tuesday, because Monday is a holiday. Ta-da! Happy Victoria Day. Take her easy, folks.